We are now starting the very last chapter of Pure Math 3. The name of this chapter, as you already know, is Complex Numbers. And the very first thing that I want you to acknowledge is that just because it is called Complex Numbers, it doesn't mean that the chapter as a whole is complicated, all right? The words are similar, but they don't mean the same. This is just a name that it was given to this particular realm of math. And the whole thing comes from this idea of what is a square root of a negative number. Until now, when you were solving equations, namely quadratics, and using, for example, the quadratic formula, every time you had a discriminant, that is what you have inside the square root was a negative number, you would stop there. You would know that that particular parabola would have no real roots, okay? And if you would plug it in your calculator, you would have math error. The thing is that we may extend what we understand of numbers to a different realm of math, in which the square root of a negative number, the square root of -1 to be more specific, is itself a number. It is called I. This is not the first time you see a letter as being a number. You know pi, you know E already. So you have the letter I, that is short for an imaginary number. You may think, okay, why am I going to study something that is called, or that is based on imaginary numbers? The thing is that the universe, particularly quantum mechanics, electronics, high-order finance, they all use models on which the existence of this number is fundamental to produce results that are compatible with real life. That's the reason why we study them. That's the reason why you study them at this point. So I is called an imaginary number, despite its name is as real or abstract as any other number, as 1, 2, e, pi, whatever. Okay, it is a number with the same quality as any other number, and it follows the same laws of algebra. So let's start with that. For example, if you have I plus I, you have 2i. Okay, and what is 2i? It is 2 times the square root of 1. But you can put this 2 inside the square root. All you have to do is to square it and put it inside. So you have square root of 4 times -1, which is square root of -4. You can do this with any other number. 4 times -1, that is going to be square root of -16. This also means that if you have square root of minus whatever, okay, whatever real number, you can write this as the square root of a times I. Okay? So, for example, if you have square root of 36i, that is going to be 6i. All right? Let's go a little bit deeper and look at what you have when you have I power to whichever number. So I to the power of 1 obviously is I. I squared is what? If you square that, that's just -1. What is I cubed? I cubed is I times I squared. So it's this times that. So it's I times -1. It's minus I. I to the power of 4. It's I squared times I squared, which is -1 times -1, which is 1. And then from this point onwards, the whole thing starts repeating itself. I to the power of 5. As you can see here, is I to the power of 6 is -1, same as there. I to the power of 7 is minus I to the power of 8 is 1, and then I to the power of 9 is going to be again I, etc. So if you have I to the power of n, all you have to do in order to figure out how much that is to divide n by 4. This is obviously if n is higher than 4, and find the remainder of this calculation. So let's say, for example, I to the power of 7. 7 divided by 4, it's 1 plus 3. 3 is the remainder. So the result of I to the power of 7 is going to be the same as I to the power of 3, as you can see here. All right? Okay. You know that real numbers, it is represented in a real line. It's just a one-dimension line where you can put every number that you can think. But you cannot put in this line an imaginary number, because an imaginary number is composed by 2 parts. One part that is real and one part that is imaginary. So I'm going back there in 30 seconds. So in order for you to be able to represent a complex number, you don't need a line, and a line won't be enough. You need a plane in which you have two lines perpendicular. This one is where you plug the real part of the number, and this one, the vertical one, is where you put the imaginary part of the number. Such a plane is called a complex plane. It's also called an Argand diagram, and this is the place where all the complex numbers are plugged in. As I told you, a complex number, represented here generally by Z, has a real part, here represented by A, and a complex part here represented by B. So, for example, this number over here, this complex number, 3 plus 2y, how would you plot that on this plane? So, the real part is 3, so you go to the real axis and you find 3, and then you go to the imaginary axis, the one over there, and you put 2. Okay, so the point is over there. All right? The real part is represented usually like this, RE of the number, which is 3 in this case, and the imaginary part 2. You have pure real numbers. If B is equal to 0, you only have the real part. And you have pure imaginary numbers. If A equals to 0, you only have the imaginary part. The number 3 minus 2y, as any other complex number, is the complex conjugate of 3 plus 2y. So what happened over here? The 3 minus 2y, what is the difference? The imaginary part has a minus now. Where is it plotted? If this is one of the numbers, the one you start with, this is what they call the conjugate, the complex conjugate of that one. And if you start with this one, that will be the complex conjugate of this. Okay? Very simple. This is going to be important later on, particularly in last lesson. But every single real number has its complex conjugate. Both together, they are called the conjugate pair, represented usually by the whatever letter you use for the complex number. You have a vertical dash, and that letter with a star, an asterisk on top. Other things you need to know, and I'm going deeper next lesson about the reason why it is so, although this one is kind of obvious. If you add a complex number to its complex conjugate, everything that you're going to have is just 2a, okay? You can think of it, just add this to that. Actually, I'm not going to talk about that. I'll talk about that next lesson. That's the purpose of the whole of next lesson, all right? But I want you to know this almost by heart because it will speed up the process of making calculations. So adding two complex numbers is just twice the real part. Subtracting two complex conjugates, I mean, not numbers, complex conjugates, you have twice the imaginary part. And if you multiply them, you'll just have a squared plus b squared. Don't forget what a is and what b is, okay? The modulus of a complex number is its distance to the origin. If you think of this complex number, what is the distance from this point to the origin over here? Again, you can think of this as a rectangle triangle, right? So it is the hypotenuse of the rectangle triangle. So it's just going to be square root of 3 squared plus 2 squared. That's what you have over here. This is valid for any complex number. Now, pay attention to one thing. You usually think of a system of axes when it comes to functions, all right? In which what you have on the y-axis is a function of what you have on the x-axis. This is not a function, okay? What you have over here is not a function of what you have over here, all right? This has the same value as the horizontal axis when you dealt only with real numbers. This is just used to represent numbers. We are not talking about functions, okay? Now that we have this distinction, it's time for us to learn a little bit about operations with complex numbers. So I'll meet you in our next lesson.